Hopefully, you all had a good lunch. It's time to get back into consuming knowledge, though, which is why it's my pleasure to introduce you to Bruce. He is, of course, Vice President over EDB. And he is here rather to talk about data horizons with Postgres. Take it away, Bruce.
Wonderful to be with you today. Let me just get my slides up and good afternoon. I hope you had a great lunch. Great. Okay, here we go. All right. So my name is Bruce Momjian. I actually live in Philadelphia. I just got back from a 30-day trip around the world, and it's good to be back for a month or two now. So I'm kind of enjoying it. I have been involved with Postgres for 26 years now, and I work for EDB for the past 16 years. This talk is one of 58 talks that I have on my website. Right here is the URL for that website. So if you'd like to see these slides, recordings of these slides, a video presentation, or you want to look at some of the 57 other presentations, feel free to go to that URL. This talk today is really kind of interesting and goes really beyond Postgres itself. Uh, Having been obviously involved in the database industry for so long, I start to kind of wonder, how did we get here? Why are we here? And of course, where are we going? Being in the Postgres leadership, knowing where you're going is important, because obviously you're looking for where your particular piece of software needs to go, and of course you also need to advise people who talk to you at conferences, and when you go to see customers, and get email about people asking for things. Where are things going? Why are we here? And how can I make the best use of my future? I have to admit, Postgres is kind of in an unusual situation here. Obviously, I've been working on it for a long time, and it it often feels like we have a crystal ball, that somehow Postgres is was in the right place when the cloud became popular. It was in the right place when data workloads started to change. It was in the right place, even for virtualization. We can't claim to have omniscience and know the future, but for some reason, we've made decisions in the past that have greatly aligned with the direction that things are going. And what I'd like to talk about today is to go backward a little bit, talk a little bit about what the traditional data needs are for organizations, and project forward of where they're going now. And of course, how is Postgres part of that? So, pretty simple outline. What are the data needs of the future? We're going to do that by looking a little bit at the traditional data needs, and try and sort of change your outlook a little bit. Having talked to so many groups, a lot of people assume that tomorrow is going to be exactly like today. They just assume that whatever needs I had yesterday, whatever challenges I had yesterday, tomorrow's going to have the same ones. And uh, I'm here to tell you that's not true. Data needs do change, database needs change, industry needs change, and the people who can kind of see those trends early are in a better situation, and a better position to adjust to those needs. I don't know how many of you know somebody who never really adjusted or have trouble adjusting. It's very frustrating because you're like, listen, you know, today we do things this way. And they're like, well, I don't really want to do that. Well, you don't really get a choice a lot of times. Yeah, for a while you can kind of go along, but eventually you're going to need to adjust to that new way of doing things. We're going to talk about how those things have changed. Then we're going to talk about how Postgres is really an ideal position to take care of future database needs. And I there's the history goes back actually to 1986 on that one. So 10 years before I started, is really where the foundations of how Postgres can meet the future data needs was set in 1986. And I'll explain that in a minute. And then we'll talk a little bit about what happens if Postgres can't, and you need another database, and what are your options there. So let's talk about the past. This computer here, I believe, is a DEC 20. This was the kind of computers we had in the 70s in a university here in Philadelphia that I was using. It was connected to dumb terminals. So think they're called the VT20, 220, or VT100 dumb terminals that were connected to this computer by a serial cable. I'm not old enough to remember punch cards. I did use a teletype a couple times in paper tape, so that a little bit I have, but my history normally started with dumb terminals. And in the dumb terminal world, you basically had a bunch of people in an office, usually in cubicles, that were connected serially or in later years via Ethernet to the computer that was in a central location. But the terminal itself was not graphic. It was just a character terminal, 80 characters across, 24 up and down, right? 80 by 24. So you had a lot. That was really the time of data entry. So you had a lot of data entry, standard forms. I was in an airport on this trip, and I still see character mode applications. If you ever look at I don't know what it's like where you are, but in some of the cities I was in, even in the United States, when I walked into Philadelphia Airport returning, I went by a terminal, and it was color, and it was but it was a standard, no graphics, character terminal, um, where you type data. Okay. And that was really dominant for the 80s and to some extent the 90s, where you started to get graphic applications, what they call, fat clients, thin clients. So things started to shift. You kind of were moving away from the character mode apps, and you had more GUIs, obviously, both at the operating system level and at the database application level. 2000s, you kind of started to get data from web browsers. People were surfing the internet. People were ordering things using web browsers. You had web apps. The big thing there was sort of shopping cart apps, right? Everyone who did retail or did some kind of product sales typically had a shopping cart app. So now at that point, you weren't getting data from dumb terminals or thin fat clients. You were now getting data from web browsers. Okay, so you had application, uh, you had data coming in from graphic apps, and it's a little different, and obviously greater volumes. And then the 2010s, things kind of just went wild open, right? So you also had you have web applications in addition to shopping cart web pages. You had web apps, right? Then you had mobile apps. You have documents that people wanted to have in the database. You have text communication, social media data coming in, geolocation data, sensor data, Internet of Things. All of a sudden, you have a lot more data coming in. It's not necessarily character based. It could be graphic based. It could be telemetry. It could be structured documents that are coming in. Again, a really different world in terms of data ingestion, right? And this, I think, really kind of displays that. So in the old days, you really only had relational data coming in, data that comes in from character apps and order entry apps. That's very structured. That works very well with a relational model. And of course, you may need to do data warehouse analysis on that there on the right. But now we have so many different types of data coming in. And this is why the sort of historical relational data that traditionally was sort of owned by DB2 and Oracle and Microsoft SQL really is no longer holding the same kind of sway that they did decades ago, because they're not necessarily able to make use of a lot of this new type of data. And then this is a huge challenge for basically people writing apps, right? So how do you actually kind of make sense of this? How do you if you're stuck sort of using a relational structure, how do you do that? So you really have two choices historically. Okay, I'm not really talking about Postgres here, but historically. So you have two structures of how to handle these new data sources, right? One option is to continue with relational. So you take your non-relational data, whether it's a document, whether it's social media, whether it's telemetry data or Internet of Things data, and you sort of squish it and you contort it into a relational structure. So you have to sort of change it to be a relational. In some case, you will lose the original structure, and because the database doesn't know the original structure, you can have limited indexing capability because you may have to had to atomize this data across a bunch of different tables, and of course then you may not be able to have the interrelationships that you had before, and some of the sort of data analysis that you typically had might be really hard. The other way of going at this problem is to basically say, okay, I got a whole lot of new data coming in, why don't I create new data stores for that? Okay. Uh, so you can go kind of wild on this and create a data store just for your JSON data, which may be from web apps and sort of web pages and browser activity maybe, and phone apps, right? And then we have a separate GIS database for your location data, and then maybe a third data store for your full text search, right? And then maybe you have some key value data that you just want to throw in there. And all of a sudden now you've got a whole bunch of different stuff going on, right? If you're kind of moving in that direction, then you kind of start to look at microservices because you now are specializing each type with its own database, and you're now probably going to have an app that only can access one of these databases. Probably the language you're using to access JIS may be different than the one you would use for JSON and so forth, right? So now you don't have a monolithic data store anymore. You're now using microservices, but you've traded that for some new problems because now data integration is going to be difficult because now you spread your data across a bunch of different services, a bunch of different databases, and if you need to pull that data together, whether it's for analysis or even for application use, that might be difficult. So now you're kind of going at a bunch of different databases all simultaneously as part of your app. Data governance can be very difficult because now you don't really know how all that data relates to each other. They're all separate. They have different retention policies. They may have different data reliability and durability guarantees. So now they could potentially get out of sync. You could have some data in one part of the system and not in another. So I'm not saying that's wrong, but I am saying that that is a very difficult problem. What's so let me just give you this slide as a way of sort of visually looking at it. In the top right, we have relational. Okay. So one option is to have basically JSON be relational and GIS be relational, and my data warehouse is relational, and even my legacy data is relational. Okay. That would be this example right here. Okay. Over here, we have a case where we have a relational system, but then we have a JSON system, and we have a GIS system. We have a separate data warehouse system, and we have a legacy system. What's really interesting about relational plus, which I'm gonna basically lump Postgres into this category, is that it basically has the ability to do relational, but it also understands JSON, it also understands GIS, it does data warehouse, and it can also do some of your legacy needs. Okay. Um, and let's talk a little bit about the different data store options that we have. So, effectively, If you're doing microservices, then you can potentially have specialized data stores because microservices typically, the way they're written, typically only have one type, deal with one type of data, and you could specialize your database to be that type of data. If you want to use relational plus, so the ability to have basically specialized data also in the same database with others, you can actually have data integration and data governance working together in your single database. So you can still store the GIS data as GIS data. You can store JSON data as JSON data. You can allow data warehouse in native data warehouse format, but you also don't need to create separate data stores for this. And now data integration becomes much easier and data governance is much easier. You can stick with your old system. Monolithic architectures work fine, but the problem there is that you don't have necessarily the ability to specialize. So Postgres is really the only database that I'm aware of that allows you to do what I'm calling this relational plus. The concept that you can effectively, you do not have to force all of your data into a relational model. You can effectively continue to use the data in its native format in Postgres, but also mix that with relational data, mix that with what we call NoSQL data, do data warehouse analysis on that, do, you know, basically allow for Internet of Things type of data. You can do all of this basically together. Now, it may sound like I'm just making this up. And why is Postgres uniquely different than other relational systems? And as I alluded to at the beginning, it's because it was designed this way. So in 1986, Michael Stonebreaker, who was at the University of California at Berkeley, decided to write what he considered to be the next generation of relational system. And he was way, way ahead of his time. So far ahead of his time that even when I started in 1996, this extendability or this relational plus capability of Postgres was really an annoyance to us in a lot of ways as a community. And only in the past 10 years have we really leveraged that extended relational capability. But let me back up. What was Michael Stonebreaker's idea in 1986? He basically had worked on Ingress, which was one of the early relational systems in the 70s. And he said, I really want to write a database that is not restricted to a fixed number of features. Okay. So I don't want a fixed number of data types. I don't want a fixed number of indexing methods. I don't want a fixed number of stored procedure languages. I don't want a fixed list of aggregates. I don't want a fixed list of uh, cast, between one data type and another. So he basically created this extendable relational database in 1986. The database didn't really take off. It was used by Illustra, which eventually became part of Ingra of Informix. But the industry really at that time, going back to my early slides, the industry at that time was still using character terminals, was still using basically very simple relational requirements, and therefore this extendability ability of the database really wasn't used in any serious way. So, um, basically, they decided that he basically created the database, and it kind of languished. It was written in '86 up to about 2001. I mean '91. I'm sorry, then they added SQL. It was originally written in Quell, and when I started in 1996, it was open source, and it was available, but there wasn't a whole lot of activity around it. It was a small group that was using it. Um, but myself and a bunch of other people said, this is really interesting project. It's an open source relational database. That's exciting. We can see how the inside of relational systems worked, because at that time I was an application developer for database applications, but I didn't understand how does SQL work? How does it understand this SQL language? How does it understand which indexes to use and which join methods to use? So that's why I got involved. Really curiosity to see the inside of a relational system. But what's really interesting about that is that uh, once we sort of got into the late 2000s and early 2010s, there was a whole need for something more. And what this something more we already had really in Postgres was a relational system that could be extended with new data types, with new indexing methods, not just B tree, with new functions, new operators, new server side languages. This chart here on the right is effectively the Postgres system tables. And while you'll see some of them look normal, like the list of users or list of tables, it also has this blue section over here, which is for specialized indexing methods, and the green section for specialized aggregates. Okay. This yellow one right here is for specialized data types, and this one is for specialized operators. In fact, I have a presentation right down here which explains some of this extendability and how it works, and some of the value of that extendability. So again, I started in 96, and this extendability was kind of there, but we didn't really use it a whole lot. But what effectively happened in the past 10, 15 years, let's say, is that you started to use the extendability of Postgres for, for actual workloads. Because again, we now had this larger type of workload, these new data ingestion requirements. So the first thing that we added was full text search, and that was done in the mid 2000s. Our Russian developers kind of, got that into Postgres. And the idea of having a full text search engine inside of a database at that time was unusual. I know you see more of them today, but it was kind of like, wow, it's kind of interesting. You'd have a relational system and a full text search engine in the same database. And to do that, we needed to add specialized indexing methods, particularly GIST, which is generalized index search, and then GIN, which is another type of index. We also have BRIN for data warehouse, and a bunch of other ones. But the point is that this extendability of the database allowed for full text search to be added. Then fast forward another 5, 7 years, and we added JSON. JSON was a huge boon to Postgres. Again, JSON in the 90s didn't exist. It was part of, it kind of came out of I believe Netscape, or but again, the idea of storing JSON in a database, you were like, "Oh, does that really make sense?" Well, now that's one of the hallmarks and one of the sort of big popularity of Postgres, because it allows people who have JSON data to store that JSON data in Postgres without forcing it into a relational structure. And of course, that relational structure, you can store the JSON document whole without changing it. And of course, because you haven't changed it, you can index it. It still appears to be a JSON document. It's kind of together. It didn't get atomized into relational. So that's a great advantage. Data warehouse, another one. Years ago, everyone had an OLT, a transactional system, and then a separate data warehouse system, right? Um, whether it was Netezza, or Green Plum, or what, I'm sorry, what, what, Teradata. They always had these data warehouse systems that kind of sit separately, and you would have to push your transaction data over to the data warehouse periodically, and then you'd run your reports over there. But people started to realize that that's not really necessary anymore, and it's kind of awkward, and you're always looking at old data. So Postgres has been, thanks to the indexing capability and the extendability of Postgres, has been basically allowing data warehouse capabilities to come into Postgres. And again, um, that URL at the bottom talks about some of those capabilities. And GIS data, which is increasingly important because of mobile apps, because of logistics, shipping, is now supported by an extension to Postgres called PostGIS, which is developed by a separate team, which understands JS much better than I'll ever understand it. But they basically have a separate project called PostGIS that you can load into Postgres and then use that as a geographical information system that also does relational, that also does full text search, that also does JSON, that also does many of these other capabilities. So, what does that mean? That means that a data row in Postgres does not need to be effectively a purely relational row. I'm not sure how many of you know, the normal forms, first norm, second normal form, third normal form of relational systems. But in Postgres, you don't need to do that. You can store an entire full text document into one of the fields. Um, you can store GIS coordinates in one of the fields. You can store JSON in one of the fields. And the beauty of that is that you have specialized indexing for example, GIS gist for the full text search. Um, you have gene indexing for the JSON-B. You can do B tree indexes. You can do hash indexes. And this is all stored in the same system. So you have consistent visibility, you have consistent durability, and you have consistent storage. So what I'm basically saying is this kind of brings all of those pieces together, where you can now kind of do everything in Postgres and have a unified system. Because before that, you effectively would have to, as I said before, have to have separate databases for all these things. And then bringing that data together was very hard. Bringing that, keeping identical durability was very hard. Visibility would be impossible. You'd have transactions happening in all these systems together. There'd no way of getting an accurate report out of that. And effectively, you could get data that it wasn't consistent across the various systems, and you'd have to deal with that or reconcile them at some point. With Postgres, you don't have to do that. You can actually kind of keep them together. Okay. However, Postgres isn't perfect. No software is, and you might want to store your data differently. So, what if there is a data warehouse optimization that is unavailable in Postgres? Postgres is a great database. It has a lot of data warehouse capabilities, but uh, if you're talking like I'd say petabytes of data, Postgres is probably not an ideal solution for that, right? Postgres is good up to the 50 terabyte, 100 terabyte range, but if you're talking petabytes, maybe you want to use a specialized database that's designed for that scale. What if you need complex full text search options? Now, as I said, Postgres has really good full text search, but as I understand it, Elasticsearch and Sphinx and some of these other ones do have more full text search options. I guess the full text search queries can be a little more complicated in those. We do have a RUM extension, which adds some of these capabilities to Postgres, but that may not be enough, right? What if you need columnar storage? This is one that's kind of an interesting case. Postgres doesn't really have a columnar option. It does have an extension called Citus, which is open source, developed primarily by Microsoft and a team there, that plugs into Postgres, which allows for columnar storage. And columnar storage is kind of interesting because it effectively allows you to store data that is not relational. So imagine you have log data, which you don't really want to like force into a relational structure, but at the same time, there might be a lot of duplicates in there. So Duplicates are really good for Columnar. Columnar kind of is designed to handle duplicates really well. So maybe you want to use Citus. If you can't, you may want to use another database for that. What if you need data sharding? If you have very high write volumes. Now, Postgres does have PG Shardman. It does allow in Postgres 14 and 15 for read sharding, but write sharding is a little more complicated. In some data workloads, you may have very high write workloads, and Postgres may not be a good fit for that. Or let's suppose you just have data in another system and you don't want to move all to Postgres, or you don't want to move it yet. So the good news is that Postgres has this thing called foreign data wrappers. Now there's a wiki here listed at the bottom, a URL that lists over 100 different data wrappers that Postgres supports. So, we support Oracle, we support Twitter, Mongo, pretty much all the relational systems. We support Amazon S3. Uh, we, I, you got to go there and look. It's the number of things that we support is really pretty unbelievable. But why do we do that? We do that because we're basically saying that we know that Postgres may not be your sole data source, and we want to create a system that allows you to not only use Postgres, but to use it with other data sources in a very efficient manner. Now, one of the interesting things about the foreign data wrappers, and something we've been working on for a bunch of years, is that Postgres doesn't necessarily just throw the query to the foreign server and require it to return a huge amount of data. We've been working over the past 5 years to improve the foreign data wrappers so much that effectively things like where clauses, order by, aggregates, and joins are actually pushed from Postgres down to the foreign server. So that effectively allows you to almost do sort of remote data analysis. So you can basically push your analysis down to, let's say, Oracle or a data warehouse system like Hadoop maybe, and that will do the work. The data comes back. You can then join that with your relational data or with data from other foreign data wrapper systems, and kind of bring them together. And that Postgres puts Postgres in this unique position. The idea that Postgres can operate at the center of your data center. We have, again, up here, we have extensions which do things like GIS and PLR, which happens to be a statistical analysis language that you can add to Postgres. We can do NoSQL type of data and sharding with Postgres. We can use data warehouse with Postgres. And if all of those things are not enough, we do have foreign data wrappers, which allow you to integrate Postgres with other data systems and basically bring that data together. Okay. So, in conclusion, basically what we have is a system that I'll back up so I can kind of show you to you. What we have here is kind of a unique system. We didn't design it this way. It came in some ways out of Berkeley with these abilities. But what has worked really well for us is that we have teams in so many different countries with so many different data needs and so many different requirements that we have gotten a lot of we sort of see Postgres as a platform, an extendable platform. In the past 10, 15 years, that extendable platform has been used mightily to effectively make Postgres that relational plus system, which allows Postgres to do relational workloads, which obviously every relational system has to do, but also allows it to mix in a lot of non relational data at the same time and do some pretty amazing things. And as I said at the beginning, it looks like we were geniuses that we now have a system that does all these things. But it was just basically the open source teams working independently over a 26-year time frame, solving problems, fixing things, adding features that new workloads were showing up People wanted to store JSON data. They wanted to store GIS data. They wanted to store full text search data. They want to do data warehousing in our existing relational system. And because Postgres was designed to be extendable, it was designed to be able to do this in a very flexible and unique way. Other relational systems are trying to do what we're doing. I know Oracle's doing it. I know MySQL's doing it. I believe Microsoft SQL is trying that too. Um, but it's hard. It's hard to take a system that wasn't designed to be extendable and make it extendable. And what you have a lot of times is that they add full text search or they add GIS, but it's kind of bolted on the side and it doesn't quite work the same way. It doesn't back up the same way. Some of the features are missing. With Postgres, that is not the case because we were designed to be extendable. A new data type that's added to Postgres will function just like an integer data type or a varchar or or a numeric data type that is part of the system or timestamp. And that has, I think, sort of solidified Postgres as sort of this next generation of relational system, and hopefully will serve it well into the decades ahead as we continue to leverage the work that was done beginning in 1986, still working on today, which is kind of crazy that we're still doing stuff that's a code base that's that old. But our open source teams are very capable. The source code's continually improved, continually overhauled, and I think we have a very bright future ahead. So with those questions, I am going to and my URL right there. I'm going to stop sharing the screen, and we're going to effectively take some questions. I hope.
Hey, great talk there, Bruce. Really informative. Loved hearing the kind of history behind Postgres as well. Just for those wondering, like where you ask questions, there's a Q&A tab. You'll see it next to the chat one. Just type anything you got in there, and then I'll relay it across to Bruce. But I thought I'd open up, just kind of expand on this kind of idea of maybe what's allowed Postgres to last so long, right? Because you said 1986. That's a very long time for a platform to keep kicking, right? It's pretty incredible at this stage so far, and you're like, this is still the future. And you lean a lot into that whole idea, essentially, of modularity, right? This kind of freedom to expand the platform. How do you decide what things to kind of bring more in-house, what things to make a core part of the product, so that you kind of keep that flexibility, but also embrace future movements?
Yeah, that's always been a struggle for us. And we continue to debate it. So let's look at full text search, for example. So full text search was done in the mid 2000s. And it originally started as an extension. So as I said before, the Russians had been interested in providing full text search. One of the first groups, I think, to sort of start to use the extendability of Postgres. And they originally had it as an extension. And it was originally actually, we have a separate contrib directory, which had sort of a full text search thing in there. Um, so I believe they developed it independently because, again, like PostGIS, you can develop a complete feature independently and just add it to Postgres. It doesn't have to be shipped by us. But in this case, they actually had it in the contrib directory, was there for a year or two. And what we eventually decided was there were so many interactions between this full text search thing and the core server that we eventually moved full text search out of this contrib directory as something that was just an extension that you added and made it part of the core server. But we continue to struggle with that. If you look at our contrib directory or what we call additional supplied modules, there's a whole probably 20 different things in there that are shipped with Postgres, but are not installed as part of the core server. And to actually install that, you need to type create extension and then that name of that additional module. And then like GIS, it becomes part of the database. It gets registered in the system tables and then it becomes part of the system. So the struggle we always have is to look at the development model that's going on for that particular piece of software and how much interaction requirement is between the two. So if we look at PostGIS, for example, which is an external project and will probably remain an external project for the foreseeable future, That's a case where the subject matter knowledge of GIS is so different than the relational systems that we work with, that they're better off taking our platform and effectively focusing on the GIS nature that I don't personally even understand fully, in terms of all of the capabilities that are there. And they just focus on that, and they can have their separate release cadence. They can fix bugs. They can add features, really independent of us. And then in the contrib area, which is the next sort of closest area, that's a facility that is useful, but probably to a niche market. It's probably not something that the average person is going to want. The only one that pops into my head is book numbers and magazine numbers. It's called ISN, ISBN. They're specialized format they have to be in. Putting that in the core server, probably not a whole lot of value. It could bloat the server and just make it's like, oh, what is that? Why do I even want it? Better to keep that external. And then, of course, something like full text search was so core to the server that we brought it in. So I would say that we're always kind of looking at that issue of is this something that should be developed on its own, should have its own release schedule, has its own subject matter excellence? Is it something that's a niche use, probably better for Contrib or PGXN, which is where a lot of our extensions live on a website, or is it something that's just so core to what everyone does? Replication being one of them. Like we used to have external replication tools like Sloaney. Over time, it became clear that that really wasn't going to scale, and we started to look at moving replication into the core server, and now we have that, both binary and logical replication, and we can't imagine having it differently. But years ago, doing things trigger based and having it external, because we didn't really understand exactly what we wanted, was the wise move. So even over time, those sort of requirements kind of come and go.
That's interesting. It sounds like you're balancing this viability between what's complementary to the core product and what's popular, right? Because if you
Right.
went for what's popular, sometimes it might betray the core kind of principles, and all of a sudden you just end up spaghetti coding your way into a mess 10, 20 years down the line.
Yeah, you usually are only going to have one way of doing something. So if you bring it into the core server, you're going to have one way.
Okay.
So in some cases, we will allow competing options to sort of percolate out there
Hmm.
until we kind of realize, okay, this is really the one approach that we think is going to be the best for most people, and then a lot of times that will come into the core server.
Okay, looks like we've got some questions come through. First off, from Mirko, they ask, could you give us a practical example or use case where a relational plus system is necessary, i.e., a situation where combining relational and non-relational data in one database is required?
Right. So let's think of let's think of like a big box retailer, okay, like Walmart or Home Depot, or those are the names I know in the United States. I don't know what names you'd have there. Carrefour, I think, is a big one in France, the only one I know in Europe. They're going to have apps for customers, customer loyalty. They're going to have shipping requirements. They're going to have logistics. They're going to have store locations. They're going to have what's my nearest store. They're going to so they're going to have social media presence, right? They're going to have complaints coming in. They're going to have documents that maybe that are part of their core server that they need to. So in a relational system, only relational, all of the GIS data coming in, all the JSON, which may be coming in from mobile apps and so forth, has to be kind of digested and broken apart into a relational structure. But obviously, once you do that, you lose a lot of the original reason it was there, and you have to sometimes reconstitute it to send it back to the application. So imagine taking JSON, bringing it in, atomizing it, and then having to do the opposite to get it back out to an application. That's obviously not going to work well. So historically, what systems have done is they've had a separate data store just for GIS and a separate data store JSON and so forth. But the problem there is that your data typically wants to be together. You want to use relationships. This customer is in this location. Is this loyalty program has this particular, you know, JSON data on their phone. And by using sort of the relational, plus you can bring those together in one system that has most of the functionality that you'd have in specialized system, but now they're all kind of together. So you can do it without it, but historically, the problem is you get these data silos where, oh, that's where all our data warehouse data goes to die, right? That's where all our
Yeah.
chats go, and over time, it sounds great when you start, but over time, those data silos can be really hard to do anything with.
Yeah, got it. That makes sense. I mean, like the metaphor would be, you can cram all your spare stuff in one room, but eventually you have to go in and find something. At that stage, not a very efficient process.
Right.
So we have a question from Tomas. They ask, does Postgres support in-memory technology? As in, can you know, for example, store tables in the memory?
So we've had that question a lot, and the issue we've always come back on is what advantages do in-memory systems have versus durable storage? So Postgres already uses, you know, obviously stores tables in memory all the time because it has a cache and so forth. There are specialized data stores I know which are only in memory, which don't have durable storage. Um, we've looked at that technology, we've looked at options there, and we've really not found a huge value over what we already have. Yes, there are some specialized structures you can do if you know you're only in memory, but overall, we don't think we're going to be moving in that direction.
Okay. We're a little bit over time now. There was one or two additional questions, but I'm sure they can reach out to you if they want to
Of
expand
course,
on the details. And I'm sure you'll be around the chat for a little bit for them to try and catch you. But Bruce, absolute pleasure. Really informative discussion. Love the responses. And hopefully be hearing more from you in the future.
great talking to you today.
Thanks, man. Okay, we're going to keep this truck moving. Apologies, folks. I had to end it there. It was a really interesting discussion we had going on, but we have another talk coming up in just a few minutes. So quickly go to the bathroom if you need to, grab yourself a drink, and be parked in your seat again, because in just a few minutes, we're going to have our next talker on the stage.